Welcome to TalkTensors, where we unpack complex machine learning papers.
And today we're looking at something really timely: uncertainty in deep generative models.
Exactly. Think large language models. They're amazing, but, well, they can make stuff up, right? The famous hallucinations.
Uh-huh. And that's a big deal if you want to use them for anything critical. You need to know how much you can trust the output.
Which brings us nicely to today's paper, Conformal Prediction Sets for Deep Generative Models via Reduction to Conformal Regression. It's by Shiroki and others from Washington State University.
Quite a mouthful, but the core idea is pretty neat.
So what's the big picture goal here?
Well, essentially it's about generating a set of possible outputs from one of these big generative models, not just one. And crucially, having a guarantee.
A guarantee? What kind of guarantee?
A guarantee that at least one of the outputs in that set meets some quality standard you define beforehand, like it's actually useful or correct.
Okay, so instead of just getting one piece of code and hoping it works.
Right. You'd get a small set of code suggestions, and you'd know with a certain probability that at least one of them is actually valid code.
That sounds incredibly useful, especially for things like AI-assisted coding or getting factual answers from LLMs.
Absolutely. The paper mentions those exact applications: code generation, natural language tasks. It's about adding that layer of trust.
It feels like a really necessary step, doesn't it? With these models getting so powerful, but also having this known failure mode.
Definitely. Quantifying the uncertainty isn't just academic. It's becoming essential for responsible deployment. This paper tackles that head on.
The authors are Human Shiroki, Devjit Raj-Roy, Yan, Venera Arnaudova, and Janardhan Rao-Dopa.
Right, from WSU. They've proposed this framework they call Generative Prediction Sets, or GPS.
GPS. Okay, so let's dig into the problem itself. Why is this so hard for deep generative models? Why can't we just use existing uncertainty methods?
Yeah, that's the key challenge. It mostly comes down to the output space.
Meaning all the possible things the model could generate.
Exactly. For text or code, the number of possible outputs is, well, practically infinite, astronomical.
Okay.
Now, standard conformal prediction methods, which are great for getting these kinds of guarantees, often need to somehow reason about that whole output space.
Which you just can't do if it's infinite.
Right. You can't list every possible sentence or program. So vanilla conformal prediction kind of breaks down.
That sounds like a fundamental roadblock. How does GPS get around that?
This is the clever bit. Instead of trying to directly form a prediction set over that massive output space.
Which is impossible.
Right. They change the question. They ask, how many times do we need to sample from the generative model to get at least one admissible output?
Admissible meaning one that meets that user-defined quality standard again. Like code that compiles or an answer that's factually correct.
Precisely. So they turn this impossible problem over infinite outputs into a problem of predicting a single number.
The number of samples needed.
Yep. And predicting a number, that sounds like a regression problem.
Okay, I see the connection.
Yeah.
Reduction to regression. How do they actually do that? What are the steps in this GPS framework?
It's basically a two-phase process. Phase one is building a special data set, what they call an augmented calibration data set.
Okay, how's that work?
They take a bunch of input examples, say coding problems where they know a good solution. For each input, they then repeatedly ask the generative model for an output.
Keep sampling.
Yeah, up to some maximum number of tries, say M, and they count how many samples it took, let's call it K, before they got one that passed their admissibility test.
So for a code problem, how many code suggestions did it take to get one that passed the unit test?
Exactly. And if they hit the maximum budget M without getting a good one, they just record a special value like M+1, basically saying didn't find one.
So they end up with pairs of input number of samples needed.
That's it. That's their calibration data. Then comes phase two.
Which uses this data.
Right. They train a model, but specifically a conformal regression model, using this calibration data. Its job is to predict, for new input you haven't seen before, that number K, how many samples you'll likely need.
And because it's conformal, it comes with that probability guarantee.
Exactly. The conformal part lets them calculate an upper bound on K, let's call it K alpha. This call tells them, if you draw call samples from the generator for this new input, you have a high probability, like 1 alpha, of getting at least one admissible output among them.
So the final output is just all the unique things generated in those call samples.
That's the prediction set. Simple as that, conceptually.
And they argue this is better than what came before. They mentioned Conformal Language Modeling, CLM.
Yeah, they draw a direct comparison. CLM was kind of the main prior approach for this.
What are the advantages of GPS, according to the paper?
Well, a big one is reducing it to standard conformal regression. That's a well-studied area.
So you can use existing tools in theory.
Exactly. Like they mention being able to handle conditional coverage more easily. It simplifies things. And, just avoiding that whole infinite output space issue is a huge conceptual simplification.
Makes sense. Anything else?
Computationally, they argue it's simpler. GPS really just calibrates one main thing, that prediction for call. CLM apparently involves tuning 3 different parameters related to filtering samples.
Simpler is often better.
And maybe most importantly for practical use, GPS works in batch mode. It decides up front, I need cost samples, and then gets them all.
Ah, unlike CLM.
CLM is apparently more sequential. It generates checks, maybe generates more. GPS's batch approach fits better with modern hardware and how people often run inference, especially of, say, LLM APIs where you might pay per call.
Right. You want to know your cost up front if possible. That's a very practical point.
Definitely. And GPS also has this built-in way to handle failure gracefully.
What if it just can't find a good answer?
Remember that M+1 value. If the predicted call ends up being higher than the original budget M, GPS can basically say, abstain.
So it knows when to quit.
It knows when it's unlikely to find a good solution within a reasonable number of tries based on the calibration data. It can output an empty set or signal failure, which is more principled than just returning potentially bad outputs.
That sounds much safer. So it predicts using conformalized quantile regression, CQR.
Yeah, that's the specific conformal technique they use. It estimates a quantile of the number of samples needed distribution, and the upper end of that quantile interval gives them call.
And the bottom line is that the set of samples is guaranteed to contain at least one good output with probability 1 alpha.
That's the core guarantee. And it's distribution-free, which is a hallmark of conformal prediction. It doesn't rely on assumptions about the model or the data distribution. Very robust.
Okay, solid foundation. Let's step back a bit. What was the landscape before GPS? What led up to this? You mentioned conformal prediction generally.
Right. CP has been around providing these guarantees for black box models, but applying it directly to generators was messy.
Because of the infinite outputs.
Yes. Also, this idea of sample coverage, maybe a good answer exists, but you just didn't happen to sample it. And semantic equivalence.
Oh, right. Multiple ways to say the same thing or write codes that does the same job.
Exactly. A generated answer might be perfectly correct functionally, but not match any specific ground truth text string exactly.
So how do people handle that semantic equivalence issue?
The paper, like some earlier work, uses that binary admissibility function, AXY. It judges the output based on criteria. Does the code work? Is the answer true? Not just string matching.
Makes sense. Focus on function, not just form.
Right. And the most direct predecessor, as we said, was CLM. Different guarantee type, pack style, more complex calibration.
And the GPS paper points out some downsides to CLM.
They do. One is that finding good CLM parameter settings isn't always possible, especially if you want really high confidence, a tiny alpha.
What is that?
Well, partly it's just the base model, right? If the generator rarely produces good stuff, no method can guarantee finding it quickly. That's fundamental.
True. Can't get blood from a stone.
But they also argue CLM's own mechanisms can be an issue. It has filtering steps to select diverse high-quality samples.
Right.
But they suggest these filters might sometimes accidentally throw away perfectly good solutions.
Oh, really? That would inflate how often I have to abstain, right?
Potentially, yes. They also mentioned CLM's abstention can be a bit all or nothing for a given setup. It either works and rarely abstains, or fails and abstains a lot. GPS aims for more nuanced, input-dependent abstention.
And it might need fewer samples sometimes.
Their experiments suggest that, yeah, especially for certain tasks. And critically, they show GPS working at tighter confidence levels where CLM struggled to even find a valid configuration.
So GPS seems designed to be more robust, efficient, and flexible in those tricky situations.
That's the claim, yeah. Building on CP fundamentals, but tailoring it smartly for generators.
Okay, moving toward the end of the paper, they touch on novel notions' future directions. What stood out there?
A key component in GPS is that admissibility estimator, F-hat. F. That's the model trained during calibration to predict the chance of getting a good sample.
Right, the thing that helps predict hay.
Exactly. And the paper notes its quality really matters. A better FEF leads to smaller prediction sets, more efficiency.
So improving have is an obvious next step.
Seems like it. They used fairly simple things like linear regression or basic neural nets on model states, but you could imagine using much more sophisticated models or training techniques for F.
Like what?
Maybe meta-learning, so FESH generalizes better across different generators or tasks, or using more complex features from the generative model if you have access. Lots of room to improve that prediction of admissibility likelihood.
Interesting.
What else? Another idea revolves around the admissibility function, AXY itself. Right now, it's fixed and binary. Yes, no, admissible or not. But what if it could be learned or refined? Or what if it wasn't binary?
How would that work? A score instead of yes, no.
Maybe. Imagine if the sets often contain things that are almost right, but fail the strict binary check. A nuanced score might capture that better, maybe leading to tighter sets focused on mostly good options, or perhaps adapt the function based on how GPS is performing.
Adapting the definition of good on the fly. That's intriguing.
It's speculative, but interesting. And they also float the idea of just trying different conformal regression techniques within the GPS framework. They use CQR, but others exist.
Could different regressors offer better trade-offs between coverage and set size, maybe?
Potentially, yeah. Different methods might suit different scenarios better, so lots of ways to potentially tune and extend the core GPS idea.
It definitely feels like a solid contribution with clear paths forward.
Agreed. It's a really significant step towards making these incredibly powerful generative models more reliable and trustworthy.
So to wrap up, this paper offers a clever way GPS to get uncertainty guarantees for deep generative models by reducing the problem to conformal regression on the number of samples needed.
Yep. Sidestepping the infinite output space issue and leveraging well-established conformal methods. The results look promising compared to prior work like CLM.
And for listeners wanting the full technical details, the proofs, the extensive experimental results, definitely grab the paper itself. The appendices are quite detailed.
Absolutely. As these models seep further into our tools and workflows, techniques like this for understanding their reliability become less of a nice-to-have and more of a necessity.
Which leaves us with a final thought. If we can get better at trusting AI outputs, thanks to methods like GPS, how does that change our relationship with AI? How does it shift how we integrate it into critical tasks?
That's the big question, isn't it? Definitely something to ponder.
Indeed. Well, that's all the time we have for this deep dive. Thanks for tuning in to TalkTensors.
Thanks, everyone. See you next time.